Page 705, section 11.7 is on graphing rational functions. Graphing rational functions, a rational function is where we have this form polynomial over polynomial. So in other words, we have some kind of a fraction going on, and in the denominator is not going to be just a number. It's not going to be like, x squared over 5. It's going to be something with a variable in the denominator, as well as probably a variable in the numerator as well, is what we're going to be looking at. So the deal is, with the variables in the denominator, it's possible that we could have values of the variable that would make our denominator equal 0, which would make this undefined. Normally we would just say it's an extraneous solution and it doesn't work. For these though, we're going to actually talk about if we were graphing these functions, what that would look like. So if you look at problem 1, right now they're keeping it simple. They're just saying what is the excluded value for the function. So basically we're just looking at this and saying our denominator can't equal 0. So for part A, our denominator is x plus 2. So we're just saying x plus 2. I would say x plus 2 cannot equal 0. So then we could say x cannot equal 2. So that's our excluded value. Excluded value is x equals 2, which basically just means x can't equal 2, otherwise denominator would be 0. We can't divide by 0, so that doesn't work. Part B, similar idea. X plus 8 cannot equal 0, so x cannot equal negative 8. That's our excluded value. So if you look at the got it number 1, they're asking for the excluded value here. So for this, our denominator is x plus 7. So x plus 7 can't equal 0. Subtract 7 says x cannot equal negative 7. So our excluded value would be x equals negative 7. Again, a lot of times I just put it like this just to make sure we don't get confused on like a solution versus something that doesn't work. But again, the book, if it says what's the excluded value, the book's going to say x equals negative 7 is our excluded value. That's the value that x cannot be equal to, otherwise our denominator would be 0. The next part talks about graphing rational functions, and this first graph over on the left here, this is the graph of y equals 1 over x. So y equals 1 over x, you can see the graph over here and the graph over here. It's kind of two different parts, and this could have arrows on the ends. 4 different places we could have arrows on the ends of that graph because it's going to keep going. And the deal with that, if you think about that, kind of like what we were just talking about, is in our denominator we have an x, just an x, and so that can't equal 0. So for this one, it's already pretty much solved. We would just say x cannot equal 0. So that's kind of what's happening here. X can't equal 0. This, right on this y-axis, that's where x equals 0. Well, x can't equal 0. So what happens is the graph gets really, really close to that, but we can never quite get to that point. So this example, I talk about these kind of like invisible fences that the graph can get close to, but it's not going to cross over. Okay, just like a dog might get close to an invisible fence, but hopefully not cross over it. And so kind of without spending too much time on that, you can think about if we're coming in from the left side of the y-axis, let's say if x is -1. Well, let's just go back up a minute. Let's say x is -3. If x is -3, that would be -1/3. So that's -3, -1/3. If x is 2, if x is -2, that would be -1/2. If x is -1, that would be -1. And then, like I said, we can't go to 0, but let's look at what if x was -1/2. So 1 divided by -1/2, if we keep change reciprocal, that would be -2. And then maybe x is -1/4. If you work that out, it's going to be -4. And we can keep getting closer. Let's say it's -1/8. Then it's going to be -8. So the deal is I keep getting really close to that y-axis. And if you'll notice, my y value keeps going down further and further. Okay? We could say x is -1/100. That'd be really, really close to that y-axis. Then y would equal -100. So you can see what's happening as we get bigger or closer to that y-axis from the left side. That just keeps going further and further into the negatives, and that's what's happening there. We get close to that, we don't cross it, and it just keeps going down. Same thing if we went from the other side. We could have x equals 2. Basically, if you look at all these things we just did, if you take off the negative sign, so let's say x is 3, then it would be +1/3. If x was 2, it would be 1/2. If x is 1, it would be 1. If x is 1/2, it would be 2. If x is 1/4, it would be 4. If it's 1/8, it would be 8. So as we get closer over here, then the y values are just going to keep getting bigger and bigger. And it's just going to keep going up. Okay? If we had 1/1000, then y would be equal to 1000. Okay, so it's like this invisible force field or this invisible fence that the line can't cross over, the graph can't cross over. So that's kind of our basis or basic form for this graph. This other one over here we've got is, instead of 1/x, we've got 1/x minus 3. So for this, if you think about that, the denominator x minus 3, well, that can't equal 0. So that means x cannot equal 3. So before we had x can't equal 0, now we have x can't equal 3. Basically, this graph, notice the numerator is exactly the same. It's just a 1 in the numerator. So this graph's going to be exactly the same as the last one, except for this is going to be shifted over. Our invisible fence is going to be shifted over. Okay. Now you might imagine we're not going to call this, actually mathematically, it's not called an invisible fence or a force field. There's actually a name for this, which is called an asymptote. And so what we're looking at here, there's the word asymptote. Okay, so that's kind of that line that it doesn't cross. So we'll just do a little bit of a definition here before we move on any further. So vertical asymptote occurs at each excluded value, and it's a dotted line that the graph doesn't cross. And I should point out as well, this vertical asymptote would be a vertical dotted line the graph doesn't cross, thus the name vertical asymptote. So if you look at problem 2, they're asking what is the vertical asymptote of this graph. And again, it's basically the same idea as what we were doing before. The vertical asymptote is going to be at our excluded value. So the denominator is x plus 2. So we could say x plus 2 can't equal 0, which means x cannot equal negative 2 if you solve that out. So our vertical asymptote is this line, x equals negative 2. Again, that's kind of that invisible fence, that force field that they are not going to be able to cross over here. So this one, similar graph to what we did earlier. They just picked some values of x on both sides of that. So they picked some numbers that were less than negative 2 over here. And then they picked 3 numbers that were greater than negative 2. And then by graphing those, we know on these graphs they're going to be curved. And so you just kind of graph the curves, and then kind of this end part, you kind of make it to where it's going to get close to this vertical asymptote, but that it's not going to cross over it. So if we look at the got it to, what is the vertical asymptote for this graph? And they want us to graph the function as well. And again, they have h of x. They could have easily just had y instead of that. That's just that function notation we've talked about. So for this, our denominator can't equal 0, so x minus 6 can't equal 0, which means x cannot equal 6, and that is going to be our vertical asymptote. So vertical asymptote would be x equals 6. So if we're going to graph this, what we want to do then is we're going to try to pick some numbers kind of close to 6 on both sides. And then we will see what kind of values we get. So what I'm going to do, I'm just going to pick some numbers kind of close to that. So let's say we pick 3, 4, and 5 as being smaller than that. And then we'll pick some numbers bigger than that. So let's say 7, 8, and 9. And then it would be substituting those back into that function. So our function y equals negative 3 over x minus 6. So if x was 3, that'd be negative 3 over negative 3, which would be negative 1. So 3, negative 1 would be one of the values here. And then I'm just going to redo over this part. Just pave over the top of that one. So if you put a 4 in, that'd be negative 3 over negative 2. We know negative divided by negative is going to be a positive, so that would be a positive 3/2 or 1 1/2. Sorry, that last one, actually, that was a negative divided by negative. That would have been a positive one. Sorry about that. And if we put in a 5, that would be negative 3 over negative 1, and that would be a positive 3. And then if we get into the other side, if we do a 7, basically what's happening now is now we have a bigger x value than what we're subtracting, which is making our denominator positive. And now so we'll have a negative divided by a positive, which will end up being a negative. So that would be negative 3. And then if we put an 8 in, that would be negative 1.5. And then if we put a 9 in, that would be negative 1. So if you'll notice, these are just opposites of what we had with the other side. So then we could go to graph this. So we've got 3, negative 1, 4, that was 3, 1, wasn't it? Okay, so 3, 1, 4, 1.5, and 5, 3. We had 7, negative 3, 8, negative 1.5, and 9, negative 1. And what we probably should have started with here is that x equals 6 was our asymptote, or vertical asymptote. So we would put a dotted line there. Dotted line showing it's not really part of our graph per se, but it gives us guidelines for where the line can't cross. And then this would, again, it just kind of approaches that, but it doesn't cross over it. So something like that. And on these graphs, there is also something going on we'll talk about later. It's called a horizontal asymptote. We'll get into that more later, but that would be also kind of a line going across. So in this case, y equals 0 would be another line that we're not crossing over.